Look up at the night sky and you are staring into a deceptive silence. For thousands of years, humanity assumed the cosmos was a serene, static void, punctuated only by gentle pinpricks of light. Modern astronomy, however, tells a radically different story. When we tune our instruments to capture infrared radiation, ultraviolet waves and faint radio emissions, the universe reveals itself not as a quiet sanctuary, but as an arena of extreme, violent, and utterly strange physics. Spectroscopic data exposes worlds where the atmospheres melt glass and rain molten metal, while deep space radio receivers catch mysterious signals pulsing across billions of light-years of empty space. The universe operates on rules that constantly challenge our understanding of chemistry, thermodynamics, and gravity. Today, we are going to explore the strangest things we have discovered in space. From invisible macrostructures that pull entire galaxies across the void, to rogue worlds drifting through perpetual frozen darkness without a star, the cosmos is filled with phenomena that test the absolute limits of scientific theory. Before we dive into these cosmic anomalies, if you enjoy exploring the deep mysteries of our universe, please feel free to leave a like and subscribe to the channel to support our research. Also, let us know in the comments below where you are listening from and what time it is wherever you are right now in the world. Deep within our galaxy, thousands of extrasolar planets have reshaped our understanding of planetary formation, atmospheric chemistry, and orbital dynamics. Among the vast catalogue of worlds discovered by space telescopes and ground-based observatories, certain exoplanets display conditions so extreme that they challenge the foundational principles of planetary science. Two of the most remarkable examples are TREES 2b, an exoplanet darker than coal, and HD 189733b, a world defined by scorching temperatures and horizontal glass rain. By analysing the light reflected and emitted by these distant bodies, astronomers have unlocked the physics behind their bizarre environments. To understand the strangeness of TREES 2b, one must first look at the astronomical surveys that located it. Discovered in 2006 by the Transiting Exoplanet Survey Network, TREES 2b orbits a Sun-like star located approximately 750 light-years away in the constellation Draco. It is classified as a hot Jupiter, a category of gas giant that shares a similar mass and radius to Jupiter in our own solar system, but orbits incredibly close to its host star. TREES 2b completes a full orbit around its star in just under 2.5 days, placing it at a distance of merely 5 million kilometers from the stellar surface. For comparison, Mercury orbits our Sun at a distance of roughly 58 million kilometers. Due to this proximity, TREES 2b is tidally locked, meaning one side permanently faces the intense heat of its star, while the other side remains in perpetual darkness. The day side of TREES 2b is baked to temperatures exceeding 980 degrees Celsius. Under such blistering conditions, traditional planetary physics would predict the presence of bright, reflective cloud decks made of ammonia, water ice, or silicates, similar to the bright clouds that give Jupiter its high albedo. In planetary astronomy, geometric albedo measures the fraction of incident light that a planet reflects back into space. Earth has a geometric albedo of roughly 0.37, reflecting 37% of incoming sunlight, while Jupiter reflects roughly 52%. When NASA's Kepler Space Telescope observed TREES 2b, measurements revealed a geometric albedo of less than 0.01. This world reflects less than 1% of the light that strikes it, making it darker than black acrylic paint, charcoal, or coal. It is officially recorded as the darkest exoplanet ever discovered. If human eyes could observe TREES 2b directly from space, it would appear as an almost completely black sphere floating against the backdrop of stars, emitting only a faint red thermal glow from its superheated atmosphere, much like a burning ember on a stove. The physical and chemical mechanism responsible for this extreme absorption of light lies in the composition of its atmosphere. Spectroscopic analysis indicates that the atmosphere of TREES 2b is rich in vaporized chemical compounds that act as light absorbers. Principal among these are gaseous sodium and potassium, along with titanium oxide and vanadium oxide in vapor form. Sodium and potassium atoms have broad atomic absorption lines in the visible spectrum, meaning they absorb vast quantities of photons across blue, green, and red wavelengths. Because the planet is so close to its parent star, These chemical species cannot condense into reflective cloud layers. Instead, they remain trapped as atomic gases in the upper atmosphere. Any optical light hitting the planet penetrates deep into this atmospheric haze and is completely absorbed before it can scatter back out into space. Furthermore, the absence of reflective clouds creates a feedback loop. The dark atmosphere absorbs even more stellar radiation, maintaining the high temperatures required to keep these light-absorbing chemicals in their vaporized state. TRES 2b stands as a testament to how thermal energy and chemical composition can strip a gas giant of its reflectivity entirely. While TRES 2b demonstrates the extremes of light absorption, another hot Jupiter, HD 189733b, demonstrates the extremes of atmospheric fluid dynamics and meteorological violence. Located approximately 64 light-years away in the constellation Vulpecula, HD 189733b was discovered in 2005 and rapidly became one of the most thoroughly studied exoplanets in modern astrophysics. Visually, data from the Hubble Space Telescope revealed that the planet possesses a deep cobalt blue color. If observed casually, one might mistake HD 189733b for a serene ocean world like Earth. However, this blue hue is not caused by liquid oceans, but rather by an atmospheric scattering effect operating under nightmare conditions. HD 189733b orbits its parent star at a distance of roughly 3.7 million kilometers, completing an orbit in just over 2.2 days. Like TRES 2b, it is tidally locked, resulting in a permanent dayside and a permanent nightside. The dayside reaches temperatures around 930 degrees Celsius, while the nightside remains significantly cooler at around 650 degrees Celsius. This massive temperature differential of nearly 300 degrees Celsius between the two hemispheres drives atmospheric weather patterns at speeds unprecedented in solar system meteorology. The fundamental laws of thermodynamics dictate that energy must transfer from regions of high temperature to regions of low temperature in an attempt to reach equilibrium. On HD 189733b, this thermal imbalance creates global wind systems driven by severe pressure gradients. Atmospheric modelling combined with Doppler velocity measurements of carbon monoxide gas in the planet's atmosphere revealed that winds blow from the dayside to the nightside at speeds reaching up to 8,700 km per hour. This is roughly 7 times the speed of sound, far surpassing the highest wind speeds ever recorded on Neptune, which reach about 2,100 km per hour. These supersonic winds interact with the chemical composition of the upper atmosphere to create a lethal meteorological phenomenon. The atmosphere of HD 189733b contains high concentrations of silicates, the chemical compounds made of silicon and oxygen that form the primary constituent of quartz, sand, and glass on Earth. At temperatures exceeding 900 degrees Celsius, these silicates do not exist as solid rock. Instead, they condense into tiny liquid silicate droplets in the upper atmosphere. As light from the host star passes through these lensed silicate particles, short wavelength blue light is scattered much more efficiently than long wavelength red light through a process known as Rayleigh scattering. This is the same optical process that makes Earth's sky appear blue, but on HD 189733b, the scattering occurs within a thick layer of liquid glass droplets, lensed through high-altitude haze, granting the entire planet its deep blue appearance. The true horror of HD 189733b lies in the coupling of these silicate clouds with the planet's extreme wind fields. As the silicate particles condense in the atmosphere, the supersonic winds blowing at nearly 9,000 km per hour carry these molten glass droplets across the planet horizontally. Rather than falling downward due to gravity like rain on Earth, the rain on HD 189733b moves sideways, whipping around the equator in a relentless cycle of horizontal glass storms. Any structure or probe entering this atmosphere would be subjected to supersonic abrasion by billions of microscopic glass shards, moving faster than a military projectile. Furthermore, observations using phase curves, which measure the light emitted by the planet as it rotates, show that the hottest region of HD 189733b is not located at the substellar point directly beneath the star, but is shifted eastward by several degrees. This phenomenon, known as an offset hotspot, provides direct physical proof of the powerful equatorial jet stream shifting thermal energy eastward faster than the planet rotates. The energy transport is so intense that it constantly drags heat away from the substellar point, maintaining the relentless wind speeds required to sustain horizontal precipitation. Both TRES-2b and HD 189733b illustrate how radiative transfer, equilibrium chemistry, and fluid mechanics interact under extreme conditions. When a gas giant is placed mere millions of kilometers from a star, standard expectations of planetary climate break down completely. Planets cease to be tranquil spheres of gas and ice, becoming dynamic physical laboratories where light is swallowed whole or transformed into supersonic storms of liquid glass. As observational technologies advance, these distant worlds continue to refine our theoretical models of planetary atmospheres across the galaxy. Beyond the realms of light-swallowing atmospheres and horizontal silicate storms lie exoplanets whose very structural frameworks challenge the classical boundaries of astrophysics. When astronomers examine the broader census of planetary bodies, they encounter object types that seem almost engineered to test the limits of gravity, materials science, and stellar evolution. Three distinct phenomena illustrate this structural diversity. The vast ring system surrounding the substellar companion J1407b, the extreme high-pressure diamond interior of the carbon planet 55 Cancri e, and the thermodynamic survival mechanisms of rogue planets drifting through interstellar space without a host star. The object designated 1SWASP J1407.93-394542.6b, commonly abbreviated as J1407b, provides a dramatic lesson in circumplanetary disk dynamics. Located approximately 430 light-years from Earth in the constellation Centaurus, J1407b orbits a young, sun-like star. When astronomers analysed light curve data from the SuperWASP survey, they detected a prolonged, highly complex series of stellar eclipses lasting over 56 days. The intensity of the star's light fluctuated wildly, dropping by up to 95% at multiple intervals. Detailed computational modelling revealed that these deep transits were not caused by a solid planet or a standard planetary atmosphere, but by a colossal system of circumplanetary rings surrounding a giant substellar body. The ring system of J1407b is staggering in scale. While Saturn boasts a ring system spanning approximately 280,000 kilometers in diameter, the ring structure of J1407b extends across an estimated 90 million kilometers. If J1407b were placed in our solar system at the position of Saturn, its rings would dominate the night sky on Earth, appearing many times larger than the full moon. The total mass of dust and ice contained within these rings is estimated to be roughly equivalent to the mass of Earth. The dynamics governing this super-ring system are rooted in the physics of protoplanetary and circumplanetary accretion disks. As a giant planet or low-mass brown dwarf forms within a star's circumstellar disk, its gravitational pull gathers surrounding gas and dust into a flattened disk orbiting the planet itself. On smaller scales, this circumplanetary disk is where regular moon systems are born. In the case of J1407b, astronomers are observing a massive circumplanetary disk in a transitional evolutionary phase. What makes the ring structure of J1407b particularly fascinating to dynamicists is the presence of distinct gaps within the dust disk. One prominent gap, spanning more than 4 million kilometers in width, suggests the presence of an exomoon in the process of clearing its orbital path. Through gravitational interactions known as orbital resonances, an embedded moon clears a gap by scattering dust particles inward or outward through gravitational perturbations, similar to how moons like Cassini and Prometheus maintain the gaps in Saturn's rings. The physical stability of such a massive ring system requires a substantial central mass. Estimates place J1407b between 10 and 40 times the mass of Jupiter, placing it right on the boundary between an oversized gas giant and a brown dwarf. Without this strong central gravitational well, the outer edges of the 90 million kilometer ring system would be stripped away by the tidal forces exerted by the host star. While J1407b showcases structural scale on a macro level, the super-Earth exoplanet 55 Cancri e demonstrates structural transformation at the atomic level. Situated 40 light-years away in the constellation Cancer, 55 Cancri e orbits its host star at an astonishingly close distance of roughly 2 million kilometers, completing a full orbit in just 17.9 hours. It possesses a mass about 8 times that of Earth and a radius twice as large, categorizing it as a super-Earth. Initial elemental abundance models of the 55 Cancri stellar system revealed a key chemical difference compared to our solar system. The host star, and consequently the protoplanetary disk from which its planets formed, possesses a significantly higher carbon-to-oxygen ratio. In our solar system, oxygen is abundant, leading to the formation of silicates, metal oxides, and water-rich planetary interiors. In a carbon-rich protoplanetary environment, however, condensed materials are dominated by carbon compounds, iron, carbides, and silicates with low oxygen content. When astrophysicists modelled the interior structure of 55 Cancri e based on its mass, radius, and carbon-rich chemical budget, they uncovered an extraordinary interior profile. The planet's immense surface gravity, combined with internal pressure conditions reaching millions of atmospheres and interior temperatures exceeding 2000 degrees Celsius, radically alters the phase state of carbon. Deep within the mantle of 55 Cancri e, elemental carbon cannot exist as graphite or simple organic compounds. Instead, the extreme hydrostatic pressure forces carbon atoms into a sp3 hybridized orbital configuration, arranging them into a dense, interlocking tetrahedral crystalline lattice. This crystalline lattice is the exact atomic structure of diamond. Theoretical interior models suggest that beneath a thin layer of atmospheric gas and graphite crust, up to 1/3 of the total mass of 55 Cancri e consists of pure diamond. The pressure-temperature gradient from the surface to the core transitions from graphite at lower pressures to solid diamond at deeper depths, surrounding a dense liquid iron-nickel core. This makes 55 Cancri e a primary candidate for a carbon planet, demonstrating how stellar chemical composition directly dictates the mineralogy and interior mechanical properties of terrestrial exoplanets. Moving away from stars entirely, modern infrared surveys have uncovered a population of worlds that exist in total isolation. Rogue planets, also known as free-floating planets. Objects like CFBD SIR 2149-0403 and SIMPJ 01365663 plus 09333473 do not orbit a host star. Instead, they wander through the interstellar medium of the galaxy alone. The existence of rogue planets is a direct consequence of early dynamical instability during planetary system formation. According to gravitational N-body simulations of young star systems, multiple giant planets forming in close proximity frequently undergo chaotic gravitational scattering events. During these violent orbital encounters, momentum is exchanged between planets, often resulting in one planet absorbing enough kinetic energy to exceed the escape velocity of the stellar system entirely. Once ejected into interstellar space, the planet is severed from its primary external energy source, the radiant light and heat of a star. Without a star to warm its surface, a rogue planet might be expected to freeze rapidly to absolute zero, becoming an inert, dead rock. However, thermodynamics and nuclear astrophysics reveal that rogue planets maintain substantial heat energy through alternative mechanisms. The primary heat source for a young gas giant rogue planet is primordial Kelvin-Helmholtz contraction. As the planet forms, gravitational potential energy is converted into thermal energy. Because gas giants are composed of compressed fluids with high thermal inertia, this heat leaks out extremely slowly over billions of years. As the planet gradually contracts under its own gravity, it continues to radiate heat into space in the infrared spectrum. For terrestrial or rock-dominated rogue planets, an additional internal heat engine operates, radiogenic heating. The decay of long-lived radioactive isotopes, primarily uranium-235, uranium-238, thorium-232, and potassium-40, generates a steady flux of thermal energy within the planetary mantle and core. On Earth, radiogenic heat accounts for roughly half of the heat escaping from the planet's interior. On a rogue planet with a substantial rocky mantle, radiogenic decay can keep the core molten and maintain internal geothermal activity for billions of years, independent of external stellar radiation. Furthermore, if a terrestrial rogue planet retains a thick, high-pressure hydrogen atmosphere, it can experience a powerful greenhouse effect. Molecular hydrogen, under high atmospheric pressures, undergoes collision-induced absorption, trapping outgoing far-infrared thermal radiation emitted by the core. Theoretical calculations suggest that a rocky rogue planet with a dense hydrogen envelope could sustain surface temperatures above the freezing point of water, potentially allowing for liquid water oceans to persist beneath thick ice sheets in the absolute dark of interstellar space, powered purely by internal geothermal and radiogenic energy. Additionally, some gas giant rogue planets generate intense magnetospheres. SIMP J01365-663 plus 0933473, for instance, exhibits a magnetic field over 200 times stronger than Jupiter's. As the planet rotates through interstellar space, the interaction between its powerful magnetic field, its ionosphere, and potentially surrounding debris or exomoons drives continuous, energetic auroral displays across its poles, emitting powerful radio bursts detectable by radio telescopes on Earth. Whether studying the gargantuan rings of J1407b, the crystalline carbon mantle of 55 Cancri e, or the radiogenically heated interiors of starless rogue worlds, these discoveries prove that planetary physics operates across a vastly broader parameter space than what is observed in our solar system. Gravity, pressure, and thermal transport combine in extreme configurations, producing structural phenomena that continue to rewrite our models of astrophysics. Transitioning from planetary dynamics to stellar phenomena, astronomers frequently encounter stars whose behavior defies standard stellar evolution models. Stars are normally predictable physical engines, balancing outward nuclear fusion pressure against inward gravitational collapse. However, when stellar systems interact with anomalous surrounding debris or undergo extreme magnetic field transformations, they produce transient events and light profiles that severely test modern astrophysics. Two of the most striking phenomena in stellar astronomy are the irregular dimming patterns of KIC 8462852 and the catastrophic energy releases produced by Magnetar starquakes. The star, designated KIC 8462852, informally known as Tabby's star or Boyajian's star, is an F-type main sequence star located approximately 1,470 light-years from Earth in the constellation Cygnus. When NASA's Kepler Space Telescope monitored KIC 8462852 during its primary mission to detect extrasolar transits, it recorded a light curve that was fundamentally different from any other star in its catalogue of over 150,000 targets. Under normal circumstances, when an exoplanet transits its host star, it produces a symmetrical, periodic drop in light intensity. These transit dips typically range from 0.01% to 2%, lasting a few hours with flat bottoms and sharp entry and exit profiles, corresponding to the disk of the planet crossing the stellar disk. KIC 8462852, by contrast, exhibited completely irregular, non-periodic dips in brightness that reached depths of up to 22%. Some dimming events lasted for days, while others persisted for weeks, exhibiting highly complex asymmetric light profiles with non-uniform entry and exit slopes. The sheer scale of a 22% brightness drop ruled out a single planet, as even a Jupiter-sized planet crossing an F-type star would only block roughly 1% of its light. Initial attempts to model the phenomenon examined a wide variety of hypotheses, ranging from instrument errors and stellar variability to speculative artificial megastructures. However, rigorous multi-wavelength photometric follow-up observations provided the key empirical evidence required to formulate a grounded astrophysical explanation. By observing KIC 8462852 across multiple electromagnetic wavelengths simultaneously, from ultraviolet and optical to infrared, astronomers measured the chromaticity of the dimming events. If a solid, opaque object were blocking the star's light, all wavelengths would be dimmed equally, a phenomenon known as achromatic dimming. Instead, observations revealed that the star dimmed significantly more in short wavelength blue light than in longer wavelength infrared light. This wavelength-dependent light attenuation is a definitive signature of Rayleigh and Mie scattering caused by microscopic dust particles. When light passes through an interstellar or circumstellar dust cloud, smaller dust grains selectively scatter shorter wavelengths of light, allowing longer infrared wavelengths to pass through with less resistance. Thermal modelling suggests that the dust surrounding KIC 8462852 consists of fine silicates and carbonaceous grains, with typical radii smaller than 1 micrometer. To explain the vast quantity of dust required to obscure up to 22% of the star's light without producing an excessive infrared excess, astrophysicists developed models involving circumstellar debris clouds produced by catastrophic breakup events. One leading mechanism involves the tidally induced destruction of an exomoon or a massive icy planetesimal. In this scenario, the orbit of a planet-moon system is perturbed by a distant companion star, driving the planetesimal or exomoon into a highly eccentric orbit that passes within the Roche limit of the host star. As the icy, volatile-rich body breaches the Roche limit, tidal forces rip the object apart, generating a vast, highly elliptical stream of fragments, gas, and microscopic dust. As this debris cloud orbits the star at a tilted inclination relative to our line of sight, the clumpy, uneven distribution of dust continuously crosses the stellar disk, producing deep, irregular, and asymmetric dips in light intensity. Over time, radiation pressure from the star gradually blows the finest dust grains out of the system, causing the dimming events to evolve and eventually fade over decadal timescales. KIC 8462852 serves as a real-time laboratory for observing the violent destruction and dust production of outer planetary systems. While KIC 8462852 demonstrates the optical chaos caused by circumstellar dust, magnetars represent the absolute upper limit of magnetic and high-energy physics in the universe. A magnetar is an ultra-dense stellar remnant, a type of neutron star formed following the core collapse supernova of a massive star. While a standard neutron star possesses a magnetic field strength on the order of 100 million Tesla, a magnetar boasts a magnetic field exceeding 100 billion Tesla. This makes magnetars the most powerful magnetic objects known in the universe, possessing magnetic field strengths 1 trillion times greater than Earth's and hundreds of thousands of times stronger than any magnetic field produced in terrestrial laboratories. The physical origin of this immense magnetic field is explained by the magneto-hydrodynamic dynamo mechanism operating during the first few seconds of a neutron star's birth. If a progenitor star's core rotates rapidly, completing a rotation in less than 10 milliseconds, convective motions within the newly formed ultra-dense nuclear fluid couple with differential rotation to amplify the seed magnetic field exponentially. This process generates an interior magnetic field capable of severely distorting the solid crust of the neutron star. The outer crust of a magnetar is an extraordinarily rigid, crystalline lattice composed of iron nuclei and relativistic, degenerate electron gas. It is estimated to be 10 million times stronger than steel. However, the immense interior magnetic field of the magnetar is not static. Due to Hall drift and ohmic dissipation, magnetic flux lines continuously twist, shear, and build up tremendous physical stress within the crust. As the interior magnetic field twists, it drags the solid crust along with it, storing vast amounts of elastic and magnetic energy over time. When the mechanical stress on the crust exceeds its physical breaking limit, the crust undergoes a catastrophic structural failure known as a starquake. During a starquake, the magnetar's crust fractures and shifts by mere micrometers or millimeters, but due to the extreme nuclear densities involved, this microscopic shift releases a staggering quantity of energy in a fraction of a millisecond. As the crust snaps, the sudden reconfiguration of the magnetic field lines launches intense Alfvén waves, transverse magneto-hydrodynamic waves, into the surrounding magnetosphere. This process is analogous to terrestrial earthquakes triggering seismic waves, but in a magnetar, the snapping of magnetic field lines accelerates charged particles to ultra-relativistic speeds. These particles interact with the magnetic field via synchrotron radiation and inverse Compton scattering, generating a blinding flash of high-energy gamma rays and hard X-rays. A famous example of this extreme energy release occurred on December 27, 2004, from the Magnetar SGR 1806-20, located approximately 50,000 light-years from Earth in the constellation Sagittarius. In less than 1/10 of a second, the starquake on SGR 1806-20 released more energy than our Sun emits in 150,000 years. The resulting giant gamma-ray flare was so powerful that it physically ionized the upper atmosphere of Earth, causing measurable disturbances in the ionosphere and saturating satellite detectors across the solar system, despite originating from across the galaxy. The physics of a magnetar starquake highlights the complex interplay between general relativity, quantum electrodynamics, and nuclear physics. Under magnetic fields exceeding 44 billion Tesla, a threshold known as the quantum electrodynamic limit, the vacuum of space itself becomes birefringent. Photons split and merge spontaneously, and electron-positron pairs are continuously created directly out of the electromagnetic field energy during a flare event. Both Tabby's star and Magnetar's illustrate how extreme physical environments redefine our understanding of stellar behavior. Whether through the massive dust streams of disrupted worlds obscuring a star's light, or the quantum electrodynamic explosions triggered by fracturing neutron star crusts, these objects reveal that stellar physics extends far beyond simple, tranquil spheres of burning gas. Beyond the violent crustal fractures of magnetars and the dusty debris clouds of disrupted worlds, stellar astrophysics reveals even more bizarre interactions between stars and their planetary or companion systems. In extreme orbital and stellar configurations, the boundary between distinct celestial bodies begins to blur. These interactions can lead to exotic hybrid structures where one star literally consumes another from the inside, or instances where a host star's intense radiation field slowly strips away the atmospheric envelope of a neighboring planet. Two prime examples of these phenomena are Thorne-Zytkow objects, hybrid stellar structures containing a neutron star core inside a red supergiant, and Gliese 436b, an exoplanet actively shedding a massive hydrogen tail like a comet. In 1977, physicist Kip Thorne and astronomer Anna Zytkow proposed a theoretical model for a hybrid star formed through a stellar collision and merger. A Thorne-Zytkow object is a stellar hybrid created when a compact neutron star is engulfed by a massive, expanding red supergiant or red giant star. While this sounds like a temporary collision that would immediately destroy one or both objects, fluid dynamics and gravitational mechanics demonstrate that such a hybrid system can reach a metastable equilibrium, existing as a distinct stellar type for hundreds of thousands of years. The formation of a Thorne-Zytkow object typically begins in a massive binary star system consisting of two high-mass stars orbiting each other. The more massive of the two stars evolves faster, undergoes a core collapse supernova, and leaves behind an ultra-dense neutron star. The remaining star evolves more slowly, eventually expanding into a red supergiant with a vast, low-density convective envelope spanning hundreds of millions of kilometers. If the initial supernova kick, or subsequent orbital decay, causes the neutron star's orbit to shrink through dynamic friction within the supergiant's outer layers, the neutron star gradually spirals inward. As the neutron star penetrates the tenuous outer atmosphere of the supergiant, it encounters severe drag forces. This process converts orbital angular momentum into thermal energy, heating the surrounding gas and drawing the neutron star inexorably toward the center of the giant star. Eventually, the neutron star sinks all the way to the host star's center, replacing the original degenerate helium or carbon-oxygen core with an exotic, ultra-dense neutron star core. The physics sustaining a Thorne-Zytkow object differs fundamentally from standard stellar fusion. In a normal red supergiant, energy is produced by nuclear fusion in shells surrounding a central helium or heavy element core. In a Thorne-Zytkow object, however, the primary energy generation engine is gravitational accretion onto the central neutron star, supplemented by exotic nuclear fusion burning in a dense layer directly surrounding the neutron star surface. As gas from the inner layers of the supergiant falls into the steep gravitational well of the neutron star, it liberates enormous quantities of gravitational potential energy. This accretion generates intense temperatures and pressures at the boundary layer of the neutron star core. Under these extreme conditions, a unique nuclear burning regime known as the rapid proton capture process, or R process, takes place. Fresh hydrogen gas drawn down from the massive convective envelope is continuously funneled into the nuclear burning zone above the neutron star, fusing into heavier elements and releasing heat that inflates the outer supergiant envelope, preventing it from collapsing entirely onto the core. Because of this unique interior engine, a Thorne-Zytkow object appears externally identical to an ordinary red supergiant in size, temperature and mass, but possesses a dramatically different chemical signature. The violent convection currents spanning the entire body of the star transport the heavy elements synthesized near the central neutron star up to the surface. Spectroscopic analysis of a candidate Thorne-Zytkow object, such as the red supergiant HV2112, located in the Small Magellanic Cloud, reveals unusually high surface abundances of lithium, rubidium, molybdenum, and yttrium. Finding these specific isotopic ratios in a supergiant atmosphere provides strong empirical evidence for an underlying neutron star engine operating within the star's interior. While Thorne-Zytkow objects represent stellar-scale parasitic engulfment, the exoplanet Gliese 436b illustrates the dramatic, destructive interaction between a host star and a close-orbiting planet. Located approximately 33 light-years from Earth in the constellation Leo, Gliese 436b is a Neptune-mass exoplanet orbiting a cool red dwarf star, or M-dwarf, designated Gliese 436. The planet orbits its star at a distance of merely 4 million kilometers, completing a full revolution in just 2.6 days. Despite being classified as a warm Neptune, Gliese 436b exhibits an atmospheric structure that is entirely unique. Observations conducted with the Hubble Space Telescope using ultraviolet spectroscopy revealed that Gliese 436b is enveloped in an enormous cloud of neutral hydrogen gas that extends across tens of millions of kilometers into space. This extended gas cloud forms a massive tail trailing behind the planet as it orbits its star, giving the exoplanet the physical appearance of a gigantic comet. The physical mechanism driving this massive atmospheric loss is photoevaporation, fueled by high-energy radiation from the host star. Although M-dwarf stars are smaller and cooler than our Sun in visible wavelengths, they emit intense flares of ultraviolet and X-ray radiation, collectively known as extreme ultraviolet flux. As Gliese 436b orbits closely to its parent star, this high-energy radiation penetrates deep into the upper layers of the planet's hydrogen and helium-rich atmosphere. When extreme ultraviolet photons strike neutral hydrogen atoms in the planetary thermosphere, they deposit energy, photoionizing the atoms and heating the gas to thousands of degrees. This extreme heat causes the hydrogen gas to expand rapidly, increasing the thermal pressure of the outer atmosphere until the thermal velocity of the gas molecules exceeds the planet's gravitational escape velocity. This phenomenon, known as hydrodynamic escape, causes the upper atmosphere to lift off the planet in a continuous, expanding planetary wind. Once the escaping hydrogen gas clears the immediate gravitational influence of Gliese 436b, it encounters the host star's radiation pressure and stellar wind, a stream of charged particles flowing outward from the M-dwarf. The radiation pressure exerted by stellar photons pushes the light hydrogen atoms backward, stretching the expanding atmospheric gas into a vast, sweeping tail. The head of this hydrogen cloud spans over 3 million kilometers across, several times larger than the host star itself, while the trailing tail extends across more than 15 million kilometers, obscuring up to 56% of the star's light in specific ultraviolet wavelengths during transit. Astrophysical calculations indicate that Gliese 436b is losing hydrogen mass at a rate of up to 100,000 tons per second. While this rate of atmospheric escape seems staggering, the total mass lost over the planet's multi-billion-year lifespan accounts for only a small fraction of its total planet mass. Consequently, Gliese 436b will not be completely stripped down to a bare rocky core, but it will continue to exist in a state of perpetual, high-volume mass loss throughout its lifetime. Gliese 436b serves as a critical empirical benchmark for studying atmospheric evolution in close-in exoplanets. It demonstrates how stellar activity can actively sculpt planetary atmospheres, transforming standard gas giant worlds into comet-like bodies, shedding vast clouds of volatile gas into the interstellar medium. Both Thorne-Zytkow objects and Gliese 436b highlight the profound impact of physical proximity in astrophysics. Whether through a neutron star consuming a supergiant from its interior, or an active M-dwarf blowing away the gaseous envelope of a Neptune-mass world, these phenomena demonstrate that celestial bodies do not evolve in isolation, but interact continuously through the extreme exchange of mass, energy, and radiation. Scaling up from individual star systems and planetary boundaries, observational cosmology shifts our focus toward the vast architectural features of the universe. When astronomers construct three-dimensional maps of the cosmic web, they discover that matter is not distributed uniformly across space. Instead, galaxies, gas, and dark matter coalesce into dense filaments and clusters, leaving behind colossal volumes of nearly empty space known as cosmic voids. These low-density regions are not merely passive, empty space. They are active, dynamic structures shaped by cosmic expansion, gravitational instability, and thermodynamic evolution. Two of the most profound macrostructures that challenge standard cosmological models are the vast Boötes Void and the mysterious cosmic microwave background cold spot, whose thermal anomaly is frequently explained through the physics of the integrated Sachs-Wolf effect within giant cosmic voids. To understand the immense scale of cosmic voids, one must first examine the Boötes Void, often referred to by astronomers as the Great Nothing. Discovered in 1981 by astronomer Robert Kirshner and his team during a redshift survey of galaxies, the Boötes Void is a spherical region of space measuring approximately 330 million light-years in diameter. It is located in the vicinity of the constellation Boötes. In a volume of space this large, standard cosmic density models predict the existence of roughly 2,000 to 10,000 bright galaxies. However, extensive deep-sky optical and radio surveys have identified only approximately 60 galaxies scattered throughout this entire 330 million light-year expanse. The physical origin of a void as immense as Boötes lies in the early acoustic fluctuations of the primordial universe and the subsequent hierarchical growth of cosmic structures driven by dark matter. In the early universe, tiny quantum density fluctuations were amplified during cosmic inflation, creating slight variations in matter density. Regions with slightly higher density exerted stronger gravitational forces, drawing matter away from surrounding lower density regions over billions of years. The formation of the Boötes Void is governed by a process known as void hierarchy and void merging. In the early stages of structure formation, numerous smaller, localized voids developed between the intersecting filaments of the cosmic web. As the universe expanded, the gravitational pull of surrounding high-density galactic filaments drew matter outward from the centers of these smaller voids toward their outer edges. This outward movement of mass is described as an effective negative pressure or an expanding void wall. When adjacent small voids expand, their surrounding matter walls gradually thin out and dissolve under the tidal forces exerted by larger surrounding cosmic structures. Eventually, these neighboring small voids merge together, forming a single, continuous supervoid. Computational n-body simulations demonstrate that the Boötes Void is not a single isolated anomaly, but rather the result of multiple smaller voids coalescing over cosmic time. The few dozen galaxies found inside the Boötes Void are arranged in a faint, tube-like filamentary structure running through its center, representing the residual remnants of the original walls that once separated the smaller voids before they merged. The interior of the Boötes Void represents an ultra-low density environment, often containing less than 10% of the mean cosmic matter density. Because matter is so sparse inside the void, the local expansion rate of space within the Boötes Void is slightly faster than the global expansion rate of the surrounding universe. This differential expansion rate occurs because the local gravitational deceleration inside the void is practically zero compared to high-density galactic clusters. Consequently, cosmic voids expand dynamically, pushing surrounding matter outward into dense filaments and superclusters, acting as key drivers in shaping the macro-scale geometry of the cosmic web. While the Boötes Void is a visible void revealed through galactic distribution surveys, another cosmic anomaly, known as the cosmic microwave background cold spot, exposes low-density macrostructures through the light of the early universe itself. The cosmic microwave background, or CMB, is the relic thermal radiation left behind from the Big Bang, emitted when the universe cooled sufficiently for neutral hydrogen atoms to form approximately 380,000 years after the beginning of time. The CMB is extraordinarily uniform, displaying a near-perfect blackbody radiation spectrum with an average temperature of approximately 2.725 Kelvin. Across the sky, tiny temperature fluctuations in the CMB exist on the scale of microkelvins, reflecting the primordial density variations that eventually seeded galaxies. However, in 2004, data gathered by NASA's Wilkinson Microwave Anisotropy Probe and later confirmed with unprecedented precision by the European Space Agency's Planck satellite revealed an anomalous region in the southern hemisphere near the constellation Eridanus. This region, known as the CMB cold spot, spans roughly 10 degrees across the sky and is significantly colder than the surrounding average temperature, exhibiting a thermal deficit of approximately 70 microkelvins, along with a larger surrounding warm ring. According to standard Gaussian cosmological models of primordial density fluctuations, the probability of such a large, deep, cold spot forming naturally from early universe quantum fluctuations is extremely low, roughly less than 1%. This discrepancy prompted astrophysicists to seek secondary mechanisms that could alter the temperature of CMB photons as they travel across billions of light years to reach our telescopes. The leading astrophysical explanation for the CMB cold spot involves a colossal intervening structure, a supervoid, interacting with light via the integrated Sachs-Wolf effect. The integrated Sachs-Wolf effect, or ISW effect, is a gravitational effect that operates when cosmic microwave background photons pass through large, evolving gravitational potential wells and hills in an expanding universe. To understand how the ISW effect alters photon temperature, one must analyze what happens when a photon traverses a cosmic void. When a CMB photon enters a cosmic void, it moves from a region of average density into a region of extremely low density. The void represents a gravitational hill, or a region of higher gravitational potential compared to surrounding dense clusters. As the photon climbs into the void, it expends energy to overcome the gravitational pull of the surrounding matter, causing its wavelength to stretch and redshifting the photon, which corresponds to a decrease in temperature. Under static conditions in a non-expanding universe, as the photon exits the void on the opposite side, it would fall back down the gravitational potential hill, gaining back the exact same amount of energy it lost when entering. The net temperature change would be zero. However, our universe is not static. It is undergoing accelerated expansion driven by dark energy. During the hundreds of millions of years it takes for a photon to travel all the way across a supervoid, spanning 1 billion light years, the accelerating expansion of the universe stretches space itself. This cosmic expansion alters the gravitational potential profile of the void while the photon is inside it. Because dark energy causes the gravitational potential of the void to decay over time, the void becomes shallower by the time the photon reaches the far edge. As a result, when the photon exits the decaying void, it receives less of an energy boost than the energy it spent entering the void. The photon exits the void with a net loss of energy, shifting to a lower frequency and a colder temperature. This energy loss is known as the late-time integrated Sachs-Wolf effect. For a supervoid to produce a thermal anomaly as pronounced as the CMB cold spot purely through the ISW effect, the void must be extraordinarily vast and empty. Observational surveys tracking galaxy distributions along the line of sight toward the cold spot, such as the Dark Energy Survey, have identified evidence for an immense supervoid, often called the Eridanus supervoid, spanning over 1 billion light-years in diameter, situated at a redshift of approximately 0.2. The physics of both the Boötes Void and the Eridanus supervoid underscores the profound impact of low-density macrostructures on our understanding of cosmology. The Boötes Void illustrates how gravitational dynamics and void merging clear out immense regions of space, concentrating galaxies along delicate boundary filaments. Simultaneously, the Eridanus supervoid and the integrated Sachs-Wolf effect demonstrate how dark energy actively modifies gravitational field strength across cosmic time, leaving a cold, observable fingerprint on the oldest light in the cosmos. These giant voids prove that the empty spaces between galaxies are as vital to understanding the fundamental parameters of the universe as the dense stars and galaxies that light up the night sky. Beyond isolated voids and individual galactic clusters lies the cosmic web, the fundamental scaffolding of the universe operating at the largest observable scales. On this megaparsec scale, matter is organized into an intricate interconnecting network of sprawling filaments, dense superclusters, and sheet-like planar walls, all bounded by vast cosmic voids. The spatial distribution and motion of thousands of galaxies across this network are governed by the gravitational influences of cold dark matter and colossal mass concentrations. Three critical structures illustrate the physics of this cosmic web: the dark matter filaments that form its spine, the enormous gravitational anomaly known as the Great Attractor within the Laniakea supercluster, and the vast southern boundary feature known as the South Pole Wall. To comprehend the large-scale structure of the universe, one must first analyze the spatial distribution of dark matter. While luminous matter, stars, gas, and dust, accounts for less than 5% of the total mass energy budget of the cosmos, dark matter comprises roughly 27%. Because dark matter interacts only through gravity and does not absorb, reflect, or emit electromagnetic radiation, it cannot be observed directly with traditional telescopes. However, computational models and observational maps based on weak gravitational lensing reveal that dark matter forms a vast three-dimensional web-like matrix stretching across billions of light-years. The physics driving the formation of this dark matter web begins in the early universe, long before the formation of the first stars. Cold dark matter, characterized by its non-relativistic velocities, collapsed gravitationally under the influence of primordial density fluctuations. Because dark matter is collisionless, meaning its particles do not experience electromagnetic forces or pressure like normal baryonic matter, it collapsed much faster into flattened two-dimensional sheets, often referred to as Zeldovich pancakes. As gravity continued to drive the collapse, these two-dimensional sheets intersected to form dense, one-dimensional filaments. Over cosmic time, baryonic gas was drawn into a deep gravitational potential wells established by these dark matter filaments. The gas cooled, condensed, and ignited to form galaxies, which aligned along the dark matter strands like glowing beads on an invisible string. Where multiple filaments intersect, the local dark matter density reaches its maximum, creating the gravitational nodes where galaxy clusters and superclusters reside. The visible cosmic web is therefore a direct tracer of the underlying invisible dark matter matrix. By tracing the motion of galaxies along these cosmic filaments, cosmologists can map the local velocity fields of the cosmic web. This mapping led to the discovery of one of the most significant gravitational dynamics in our cosmic neighborhood, the Great Attractor. For decades, astronomers measuring the movement of the Milky Way, the Andromeda Galaxy, and neighboring members of the local group noticed a systemic anomaly. Relative to the uniform expansion of the universe described by Hubble's law, our entire galactic region is moving at a peculiar velocity of approximately 600 kilometers per second toward a specific point in space located roughly 200 million light-years away in the direction of the constellation Centaurus. This directional velocity vector pointed toward a massive gravitational anomaly hidden behind the plane of the Milky Way. This region of the sky is known as the zone of avoidance because the thick dust, gas, and dense star fields of our galaxy's disk obscure optical observations of the space beyond. When radio and infrared surveys, such as the zone of avoidance redshift surveys using the Parkes Observatory, penetrated this dust barrier, they confirmed the presence of a massive concentration of mass, the Great Attractor. The Great Attractor is not a single giant object, black hole, or hyperdense star. It is a diffuse, region-wide gravitational potential well situated at the centre of the Norma cluster and surrounding galaxy groups, containing a mass equivalent to tens of thousands of Milky Ways. To understand its true role, cosmologists re-evaluated the definition of a supercluster based on velocity fields rather than simple spatial distribution. In 2014, a team of astronomers led by Brent Tully mapped the peculiar velocities of over 8,000 galaxies in our local universe. By calculating the flow lines along which galaxies are moving under the influence of gravity, they delineated the boundaries of our home supercluster, naming it Laniakea, a Hawaiian term meaning immense heaven. Laniakea spans more than 500 million light-years across and contains the mass of roughly 100 quadrillion suns, encompassing over 100,000 galaxies. Within Laniakea, all galaxy motions are directed inward along cosmic web filaments toward the central gravitational basin of the Great Attractor, much like water flowing down a watershed into a central valley. The Great Attractor is simply the primary gravitational focus of the Laniakea supercluster. However, precise measurements of velocity fields show that even the Great Attractor itself, along with the entire Laniakea supercluster, is being pulled toward an even larger mass concentration located further away, the Shapley supercluster. This hierarchical flow demonstrates how gravitational potential wells operate across nested scales within the cosmic web, with local filaments funneling matter into superclusters, which are in turn drawn toward colossal meganodes across hundreds of millions of light-years. While Laniakea defines our local watershed, another immense macrostructure discovered in 2020 defines the southern boundary of our cosmic neighborhood, the South Pole Wall. Discovered using galaxy redshift surveys combined with peculiar velocity measurements from the Cosmic Flows 3 catalogue, the South Pole Wall is one of the largest continuous cosmic structures ever identified in the universe. The South Pole Wall is a gargantuan filamentary wall of galaxies curving across the sky, anchored near the celestial South Pole. It extends across a distance of roughly 1.4 billion light-years, rivaling the size of famous macrostructures like the Sloan Great Wall and the Hercules Corona Borealis Great Wall. Despite its immense size, the South Pole Wall remained hidden from astronomical surveys for decades because significant portions of its structure lie directly behind the dense dust clouds of the galactic plane within the southern sky's zone of avoidance. By utilizing peculiar velocity analysis, astronomers mapped the hidden wall without needing to see every individual galaxy optically. Galaxies located near a massive structure experience gravitational acceleration toward the structure, causing their measured redshift to deviate slightly from the smooth cosmological expansion rate. By compiling these velocity deviations across thousands of galaxies, scientists reconstructed the density field, revealing the South Pole Wall as an uninterrupted arc of matter sweeping through space. The South Pole Wall forms a massive galactic barrier that borders the Laniakea supercluster. It consists of thousands of galaxies bound within dense filaments that enclose local cosmic voids, acting as a structural wall of the cosmic web in the southern hemisphere. Its immense scale provides a direct physical test for the standard cosmological model, known as the lambda cold dark matter model. According to the cosmological principle, on sufficiently large scales, typically accepted as above 300 million light-years, the universe should appear homogeneous and isotropic, meaning matter should be evenly distributed in all directions. Structure as large as the South Pole Wall, spanning over 1.4 billion light-years, approach the theoretical upper limit for how large a gravitationally bound structure can grow since the Big Bang, given the age of the universe and the speed of light. The existence of dark matter filaments, the Laniakea watershed driven by the Great Attractor, and the vast expanse of the South Pole Wall demonstrates the dynamic complexity of the cosmic web. Dark matter acts as the primary gravitational framework, pulling baryonic matter into dense strands and walls, while superclusters function as giant gravitational basins, funneling galaxies along thousands of light-years of space. As observational techniques penetrate deeper into obscured regions of the sky, these macrostructures continue to map the ultimate architectural limits of our universe. Turning our attention to the high-energy centers of galaxies, supermassive black holes represent some of the most concentrated engines of gravitational and radiative power in the cosmos. While black holes are famously known for consuming surrounding matter, the physics of accretion and frame dragging allows these monsters to return colossal amounts of energy back into their environments. When supermassive black holes interact violently with their surrounding intergalactic gas, or merge with other black holes in asymmetric collisions, they drive events that reshape entire galaxy clusters. Two prime examples of these extreme energetic phenomena are the historic record-breaking eruption within the Ophiuchus galaxy cluster and the gravitational wave recoil mechanism that can eject supermassive black holes entirely from their host galaxies. The eruption recorded in the Ophiuchus galaxy cluster, located approximately 390 million light-years from Earth, represents the single most energetic explosion ever discovered in the universe since the Big Bang itself. Galaxy clusters are the largest gravitationally bound structures in the cosmos, containing hundreds or thousands of galaxies embedded in a vast atmosphere of superheated gas known as the intracluster medium. This intracluster medium shines brightly in the X-ray spectrum, emitting thermal radiation at temperatures reaching tens of millions of degrees Celsius. When astronomers analysed archival X-ray data gathered by NASA's Chandra X-ray Observatory, alongside radio data from the Murchison Wide Field Array and the Giant Metawave Radio Telescope, they uncovered an extraordinary cavity embedded within the hot X-ray plasma of the Ophiuchus cluster. This cavity was so immense that a single galaxy could easily fit inside it, measuring over 1 million light-years across. For a cavity of this scale to exist, an incomprehensible amount of physical force was required to carve out the dense, high-pressure intracluster gas. The origin of this cavity was traced directly to an active galactic nucleus situated within the central dominant galaxy of the cluster. At the core of this galaxy sits a supermassive black hole that underwent a historic period of hyperaccretion. The physics powering this cluster-scale eruption is driven by the magneto-hydrodynamic acceleration of relativistic jets. As vast quantities of intergalactic gas fell toward the supermassive black hole, an accretion disk formed around the event horizon. Through the Blandford-Snarchek process, the black hole's rotational energy, combined with intense magnetic fields anchored in the inner accretion disk, funneled ionized matter outward along the black hole's spin axis at speeds approaching the speed of light. These relativistic jets slammed directly into the surrounding intracluster medium. Over tens of millions of years, the continuous ram pressure exerted by the jets acted like a cosmic snowplow, pushing away billions of solar masses of hot plasma and carving out a gigantic vacuum bubble in the intergalactic gas. The energy required to displace this amount of plasma and create a 1 million light-year cavity is estimated at roughly 5 times 10 to the 58 joules. This amount of energy is 5 times greater than the previous record holder, the MS-0735, 6 plus 7,421 cluster eruption, and millions of times more energetic than typical stellar supernova explosions. As the relativistic jets gradually lost power and shut down, the carved-out cavity remained. The cavity is filled with ultra-relativistic electrons radiating low-frequency radio waves via synchrotron radiation as they spiraled through weak magnetic fields trapped inside the bubble. The Ophiuchus eruption demonstrates the immense feedback role that supermassive black holes play in regulating cluster-scale gas dynamics. By carving giant cavities and driving shockwaves through the intracluster medium, black hole jets prevent intergalactic gas from cooling and collapsing to form new stars, effectively shaping the growth and evolution of entire galaxy populations across megaparsec scales. While the Ophiuchus eruption highlights the outwards radiative and mechanical power of black hole jets, an equally violent phenomenon occurs when supermassive black holes themselves are physically displaced through gravitational wave recoil dynamics. In the active centers of merged galaxies, supermassive black hole binaries eventually form and spiral inward toward a final collision, releasing staggering quantities of gravitational radiation into the fabric of spacetime. Under specific physical conditions, this merger event converts into an asymmetric launcher, firing the newly formed supermassive black hole into interstellar space at speeds exceeding several thousand kilometers per second. This process is known as gravitational wave recoil, or a black hole kick. To understand how a supermassive black hole, possessing millions or billions of solar masses, can be ejected from its host galaxy, one must analyze the momentum balance of gravitational wave emission during the final plunge phase of a binary black hole merger. Gravitational waves carry both energy and linear momentum away from the merging binary system. If the binary system is completely symmetric, meaning both black holes have identical masses and zero or parallel quantum-like spins, the gravitational radiation is emitted isotropically in all directions, resulting in zero net momentum imparted to the remnant black hole. However, if the merging binary black hole system is asymmetric, featuring unequal mass ratios or, more importantly, misaligned, highly tilted black hole spins relative to the orbital plane, the radiation of gravitational waves becomes severely anisotropic. During the final orbits before the ringdown, known as the plunge phase, the misaligned spins cause the orbital plane to undergo complex precession. This precessing motion breaks the spatial symmetry of the emitted gravitational field. The binary system radiates gravitational waves preferentially in one specific direction. According to the conservation of linear momentum, the asymmetric emission of gravitational wave momentum in one direction requires the newly merged black hole remnant to experience an equal and opposite physical recoil kick in the opposing direction. Theoretical calculations based on numerical relativity simulations reveal that while mass asymmetries alone produce modest recoil velocities of a few hundred kilometers per second, spin-induced frame-dragging asymmetries produce extreme recoil velocities. When two rapidly spinning supermassive black holes merge, with their spin vectors lying in the orbital plane and oriented in opposite directions, a configuration known as the superkick configuration, the gravitational wave recoil velocity can reach up to 5,000 kilometers per second. A recoil kick of 5,000 kilometers per second far exceeds the escape velocity of even the most massive giant elliptical galaxies, which typically feature escape velocities between 1,000 and 2,000 kilometers per second. Consequently, an ejected supermassive black hole will break free from its host galaxy's central core, drifting through the galactic halo or escaping into intergalactic space as a rogue supermassive black hole. Astronomical candidate observations, such as the quasar 3C186, located approximately 8 billion light-years away, provide strong empirical support for this gravitational recoil mechanism. Optical and X-ray observations of 3C186 reveal an active quasar displaced by over 35,000 light-years from the center of its host galaxy, moving outward at a measured velocity of nearly 5 million kilometers per second. As a recoiling black hole travels away from the galaxy's center, it carries along a compact accretion disk composed of gas and stars trapped deep within its tight gravitational sphere of influence. This bound gas continues to feed the black hole, generating bright quasar light far outside the galactic nucleus, where such active engines are normally anchored. Once this bound reservoir of gas is depleted, the ejected black hole becomes completely dark, drifting silently through the intergalactic void as a naked, supermassive gravitational anchor. The physics of both the Ophiuchus cluster eruption and gravitational wave recoil showcases the extreme dynamic power of supermassive black holes. The Ophiuchus cavity proves that relativistic jets can physically displace plasma across 1 million light-years, carving gigantic voids in the intracluster medium. Simultaneously, gravitational recoil dynamics demonstrate how the asymmetric radiation of spacetime itself can launch billions of solar masses out of a galaxy. These phenomena confirm that supermassive black holes are not merely passive central mass points, but active physical drivers, capable of transforming both host galaxies and the vast intergalactic structures surrounding them. Deep within the cores of active galaxies, supermassive black holes act as the primary power generators for quasars, short for quasi-stellar radio sources. Quasars represent the most luminous, persistent, non-transient engines in the observable universe, emitting light so intense that a single quasar can outshine an entire galaxy containing hundreds of billions of stars combined. This staggering energy output, reaching power levels exceeding 10 to the 46 watts, is not produced by nuclear fusion inside stars. Instead, it is generated through the converting of gravitational potential energy into electromagnetic radiation within the ultra-dense environment of a quasar accretion disk. Objects such as J0313-1806, the most distant quasar ever discovered, and 3C273 illustrate the extreme thermodynamic, fluid, and electromagnetic processes operating around these monster engines. To understand how a quasar operates, one must examine the accretion disk that surrounds a central supermassive black hole. As interstellar gas, dust, and disrupted stars fall into the deep gravitational potential well of a black hole, possessing hundreds of millions to tens of billions of solar masses, the incoming matter cannot sink directly past the event horizon. Because the gas carries angular momentum relative to the central singularity, it settles into a flattened, rapidly rotating circumhole structure known as an accretion disk. The physics governing matter moving within a quasar accretion disk is described by thin disk accretion theory, famously formalized in the Shakura-Sunyaev alpha disk model. Matter within the disk moves in differential Keplerian orbits, meaning that gas rings orbiting closer to the central black hole rotate at significantly higher orbital velocities than gas rings situated further out in the disk. At the inner edge of the accretion disk, near the innermost stable circular orbit, gas rotates at relativistic velocities approaching a significant fraction of the speed of sound and the speed of light. This extreme differential rotation creates immense shear forces between adjacent concentric rings of gas, moving at different orbital speeds. Fluid dynamics dictates that when gas layers slide past one another at varying velocities, internal friction occurs. In standard fluids, simple molecular viscosity generates friction. However, in the hyperdense, highly ionized plasma of an accretion disk, molecular viscosity is vastly insufficient to drive the observed mass inflow rates. Instead, the required shear stress and energy dissipation are generated by a powerful magnetic instability known as the magnetorotational instability, or MRI. Because the accreted plasma is fully ionized into free electrons and atomic nuclei, it is deeply coupled to the magnetic field lines threading the disk. As inner plasma layers rotate faster than outer layers, they stretch and twist the magnetic field lines along the azimuthal direction. This stretching creates magnetic tension, which acts as an effective turbulent magnetic viscosity. The magnetorotational instability drives intense turbulent motion within the plasma, causing adjacent gas layers to rub against one another with extreme physical friction. This magnetic friction exerts a drag torque on the inner gas rings, causing the orbiting plasma to lose angular momentum. As the gas loses angular momentum, it spirals inward toward the black hole, releasing vast amounts of gravitational potential energy in the process. This liberated gravitational potential energy is converted directly into thermal heat energy via viscous and magnetic dissipation within the disk. The thermal energy density within the inner accretion disk reaches staggering proportions, heating the plasma to equilibrium temperatures ranging from hundreds of thousands to tens of millions of degrees Celsius. At these extreme temperatures, the accreted gas transforms into a superheated, fully ionized plasma state, radiating thermal photons continuously across the entire electromagnetic spectrum. The radiative spectrum emitted by a quasar accretion disk spans from optical and ultraviolet wavelengths to high-energy X-rays and gamma rays. The cooler outer regions of the disk radiate predominantly in the optical and infrared spectra, while the scorching inner regions emit blinding ultraviolet radiation. Directly above the inner disk, a region of hot, low-density relativistic electrons known as the corona, inverse Compton scatters lower-energy optical and ultraviolet photons, boosting them into hard X-ray energies. The total luminosity generated by a quasar accretion disk depends on two primary variables: the mass of the central supermassive black hole and the mass accretion rate, which measures the amount of mass falling into the disk per second. When the mass accretion rate reaches its maximum theoretical limit, known as the Eddington limit, the outward force exerted by radiation pressure balances the inward pull of gravity. In a quasar operating near or at the Eddington limit, radiation pressure is so immense that photons streaming outward from the inner disk literally push against the infalling electrons through Thomson scattering. If the accretion rate exceeds the Eddington limit, the radiation pressure overcomes gravity, blowing away surrounding gas and halting the mass accretion process. For the largest quasars, such as J0313-1806, which houses a supermassive black hole of 1.6 billion solar masses, just 800 million years after the Big Bang, the central engine must consume hundreds of solar masses of gas every single year to sustain its blinding luminosity. The efficiency of energy conversion inside a quasar accretion disk far surpasses any other known physical process in non-quantum astrophysics. For comparison, nuclear fusion inside the core of a star converts approximately 0.7% of rest mass energy into electromagnetic radiation through the fusion of hydrogen into helium. By contrast, a non-rotating Schwarzschild black hole converts roughly 5.7% of accreted rest mass energy into radiation via its accretion disk. However, if the central supermassive black hole is rapidly spinning, a Kerr black hole, frame-dragging effects pull space itself into rotation, shifting the innermost stable circular orbit much closer to the event horizon. In a maximally spinning Kerr black hole, gas can remain in a stable accretion disk much deeper within the gravitational potential well before falling across the event horizon. This allows magnetic friction to extract significantly more energy, boosting the rest mass energy conversion efficiency of the quasar accretion disk up to 42%. This 42% efficiency means that almost half of the mass falling into a rapidly spinning supermassive black hole is transformed directly into pure blinding light before ever crossing the event horizon. This extreme thermodynamic conversion explains how quasars, like 3C273, can emit more light than thousands of galaxies, while operating within a volume of space no larger than our own solar system. Furthermore, the immense radiation pressure and magnetic fields generated within the inner accretion disk do not merely produce light, they actively sculpt the surrounding host galaxy. Relativistic wind fields, driven by extreme photon pressure, alongside collimated magnetic jet structures, blow vast channels through the interstellar gas of the host galaxy. This active galactic nucleus feedback sweeps away cold molecular hydrogen clouds, depriving the galaxy of the raw materials needed to form new stars, and permanently altering the evolutionary trajectory of the galaxy. The physics of quasar accretion disks highlights the unmatched efficiency of gravitational energy extraction in the universe. Through the mechanics of magneto-rotational instability, magnetic friction, and frame dragging around spinning Kerr black holes, these superheated plasma disks transform infalling matter into radiative engines that illuminate the far reaches of cosmic history. Quasars prove that gravitational collapse, when combined with plasma turbulence and relativity, represents the ultimate power generator in the cosmos. Turning our attention from distant active galactic nuclei to transient anomalies passing through or near our own stellar neighbourhood, astrophysicists frequently encounter phenomena that challenge standard orbital mechanics and wave emission models. Transient cosmic events provide critical insights because they represent brief, dynamic windows into high-energy physics and interstellar chemistry. Two of the most enigmatic phenomena discovered in recent years are the anomalous non-gravitational acceleration of the interstellar visitor Oumuamua and the millisecond duration high-energy radio bursts known as fast radio bursts. In October 2017, astronomers operating the Pan-STARRS telescope in Hawaii detected a small, fast-moving celestial object passing through our solar system on an extremely unbound, hyperbolic trajectory. Designated 1I/2017 U1 and named Oumuamua, it was officially recognized as the first confirmed interstellar object ever observed passing through our stellar system. Spectroscopic and light curve analyses revealed an elongated or pancake-like object, roughly 100 to 400 meters in length, displaying extreme brightness variations as it tumbled through space every 7 to 8 hours. What baffled dynamicists was not merely its hyperbolic orbit, which indicated an origin outside our solar system, but its trajectory as it departed the inner solar system after passing perihelion. Careful orbital tracking by ground-based observatories and space telescopes demonstrated that Oumuamua was accelerating away from the Sun faster than could be accounted for by the gravitational pull of the Sun, planets, and major asteroids combined. Under standard celestial mechanics, non-gravitational acceleration in small solar system bodies like comets is driven by outgassing. As a comet approaches the Sun, solar radiation heats volatile surface ice, causing water, carbon monoxide, and carbon dioxide to sublimate directly into gas. This expanding gas vents into space, creating a visible atmosphere, or coma, alongside a dust tail. The jet action of this escaping gas acts like a miniature rocket engine, imparting a continuous physical thrust that pushes the object slightly off a purely gravitational trajectory. However, extensive deep sky imaging using the Very Large Telescope and the Hubble Space Telescope revealed no trace of a coma, dust cloud, or gaseous tail surrounding Oumuamua. The object appeared completely inert, lacking the visible signatures of active cometary outgassing. This lack of visible dust led to intense debate regarding the physical force driving its non-gravitational acceleration. The physical explanation for Oumuamua's non-gravitational acceleration lies in the thermal outgassing of invisible, highly volatile molecular gases stored beneath a radiation-altered crust. Over millions or billions of years spent travelling through the interstellar medium, cosmic rays penetrate the outer layers of interstellar icy planetesimals, inducing radiolytic chemical processing. This cosmic radiation breaks apart complex icy molecules, generating trapped molecular hydrogen and carbon monoxide gas matrices beneath a dark organic-rich mantle. As Oumuamua approached the Sun, solar heat penetrated this protective crust, warming the trapped volatile pockets. The trapped molecular hydrogen and carbon monoxide gas sublimated rapidly, escaping through microscopic fractures in the surface crust. Because molecular hydrogen gas is exceptionally light and invisible in standard optical wavelengths, it produced zero detectable dust or visible coma, while still generating sufficient kinetic thrust to accelerate the small body away from the Sun. The orientation and spin dynamics of Oumuamua allowed this subtle dust-free outgassing mechanism to impart a smooth, non-gravitational acceleration, confirming that Oumuamua was a volatile-rich interstellar planetesimal undergoing thermal evolution. While Oumuamua represents a physical visitor traversing our planetary system, fast radio bursts, or FRBs, represent transient electromagnetic phenomena originating across cosmological distances. First discovered in 2007 in archived data from the Parkes Observatory, a fast radio burst is an extremely intense, highly dispersed pulse of radio emission, lasting only a few milliseconds. Despite their fleeting duration, the total energy released during a single fast radio burst is staggering, equivalent to the energy output generated by our Sun over several days or weeks. The primary physical signature used to analyse fast radio bursts is their dispersion measure. As a radio pulse propagates across billions of light-years of interstellar and intergalactic space, it interacts with cold, ionized plasma in the intergalactic medium. The free electrons in this plasma interact with the electric field of the radio wave, causing higher frequency radio waves to travel slightly faster through space than lower frequency radio waves. When a radio telescope detects a fast radio burst, the high frequencies arrive at the detector milliseconds before the lower frequencies, creating a characteristic sweeping curve on a frequency-time spectrogram. The magnitude of this frequency delay, the dispersion measure, is directly proportional to the total column density of free electrons the radio pulse encountered along its line of sight. Measuring high dispersion measures confirmed that the vast majority of fast radio bursts originate far outside the Milky Way, at cosmological distances spanning billions of light-years. To generate a millisecond-long radio burst powerful enough to be detected across billions of light-years, the emission mechanism must operate within a compact region of space no larger than a few hundred kilometers across, governed by intense magnetic fields and coherent emission processes. The leading physical framework for fast radio bursts involves active magnetars, highly magnetized neutron stars operating in extreme environments. In 2020, astronomers detected a bright millisecond fast radio burst designated FRB 200428, originating from a known magnetar within our own galaxy, SGR 1935 plus 2154. This event provided direct observational proof that magnetars are a primary source of fast radio bursts. The physics powering an FRB within a magnetar atmosphere is driven by relativistic magnetohydrodynamic shockwaves and magnetic reconnection events. When a starquake fractures the solid iron crust of a magnetar, sudden twisting of the ultra-strong magnetic field lines releases an intense flare of relativistic electrons and positrons into the surrounding magnetosphere. This expanding cloud of relativistic plasma slams into the surrounding stellar wind, or previous explosion remnants, at speeds near the speed of light, driving a relativistic magnetohydrodynamic shockwave outward. As the shockwave propagates, it generates plasma instabilities that trigger coherent synchrotron maser emission. Unlike incoherent radio emission, where individual charged particles radiate independently, coherent maser emission occurs when bunches of relativistic electrons oscillate in phase within intense magnetic field lines. This phase-coherent oscillation amplifies the radio waves exponentially, generating an ultra-bright, highly collimated beam of millisecond radio energy, capable of traversing cosmological voids. Furthermore, some fast radio bursts exhibit repeating pulses, such as FRB 121102, while others appear as single, non-repeating events. The repeating sources allow astronomers to track their precise location back to dwarf host galaxies and dense star-forming regions, indicating that active, highly magnetized young neutron stars embedded in supernova remnants serve as the engines powering these continuous cosmic radio bursts. Both Oumuamua and fast radio bursts demonstrate how brief, transient events offer valuable insights into cosmic physics. The non-gravitational acceleration of Oumuamua reveals the complex chemical outgassing of volatile-rich bodies formed in distant planetary systems, while fast radio bursts showcase the extreme coherent plasma radiation produced by magnetars across cosmological space. In the history of observational radio astronomy, few transient events have captured as much scientific interest or generated as much debate as the signal detected on August 15, 1977. Received by Ohio State University's Big Ear radio telescope during a routine sky survey, the narrowband signal lasted for 72 seconds and exhibited an unprecedented signal-to-noise ratio. Astronomer Jerry Ehman famously circled the alphanumeric code representing its intensity on the computer printout, writing the word "wow" in the margin. For decades, the WOW signal stood as an unexplained anomaly, often cited in discussions of potential extraterrestrial technology. However, rigorous modern radio astronomy and physical analysis re-evaluate this event through the lens of natural radio emission processes, interstellar scintillation, and transient astrophysical phenomena. To evaluate the WOW signal scientifically, one must first understand the observational parameters and hardware design of the Big Ear telescope. The Big Ear was a transit instrument, meaning it was fixed in orientation and utilized the rotation of Earth to scan the sky across a narrow strip. Its antenna feed horn swept across a given point in space over a duration of exactly 72 seconds, matching the time it took for a distant point source to pass through the telescope's directional beam pattern. The recorded signal rose in intensity for 36 seconds, reached a distinct peak, and then symmetrical decreased for another 36 seconds. This bell-shaped intensity curve confirmed that the emission originated from a discrete, point-like source in space, rather than an artificial terrestrial transmitter moving near the observatory. The most critical physical characteristic of the signal was its frequency. The Big Ear recorded the signal at approximately 1420.405 MHz. In radio astrophysics, this specific frequency corresponds directly to the neutral hydrogen line, or the 21 centimeter line. The 21 centimeter line is produced by the hyperfine spin-flip transition of neutral atomic hydrogen, the most abundant element in the universe. When an electron in a ground-state hydrogen atom spontaneously flips its spin orientation relative to the proton, it releases a photon with a precise wavelength of 21.106 centimeters, corresponding to a frequency of 1420 MHz. Because neutral hydrogen gas permeates interstellar space throughout the galactic plane, the 21 centimeter line serves as a fundamental benchmark for mapping the structure, velocity fields, and dynamics of the Milky Way. To prevent interference with scientific observations of this cosmic gas, international radio spectrum management regulations strictly protect the 1420 MHz frequency band, prohibiting terrestrial, commercial, and military broadcasts. The narrow bandwidth of the WOW signal, measuring less than 10 kHz wide, was particularly striking. Natural astronomical radio sources, such as thermal emission from gas clouds or non-thermal synchrotron radiation from supernova remnants, typically emit broad-spectrum radio noise spanning many megahertz or gigahertz. Narrowband signals, by contrast, concentrate energy into extremely tight frequency channels, which led early researchers to question whether natural processes could produce such focused emission. However, modern physical models demonstrate that natural astrophysical events can produce brief, ultra-narrowband radio emissions when combined with interstellar propagation dynamics. Primary among these mechanisms is interstellar scintillation, a wave propagation effect analogous to the twinkling of stars in visible light, but operating on radio wavelengths within the ionized interstellar medium. Interstellar space is not an absolute vacuum. It is filled with a low-density, turbulent, ionized plasma known as the interstellar medium. As a narrowband or coherent radio signal propagates through this plasma, it encounters localized fluctuations in electron density. These microscopic electron density variations alter the refractive index of the medium, causing the radio wavefronts to bend, scatter, and interfere with one another. This process, known as diffractive interstellar scintillation, creates an intricate three-dimensional interference pattern of bright and dark intensity focal spots sweeping across space. If a distant, stable, natural radio source emits a continuous pulse, and a high-density focal patch of the scintillation pattern sweeps across Earth's position relative to the receiving radio telescope, the observed signal strength can be amplified by orders of magnitude for a brief period before rapidly fading away. Recent astrophysical research into transient radio emissions suggests several natural phenomena capable of generating the underlying source emission that underwent interstellar scintillation during the 1977 Big Ear observation. One prominent hypothesis involves a rare, high-energy event occurring within a cold, neutral hydrogen cloud, or a high-velocity cloud passing through the galactic halo. When a transient high-energy burst, such as a soft gamma-ray repeater flare, a Magnetar starquake, or a stimulated maser emission from an interstellar gas cloud, interacts with a dense cloud of neutral hydrogen atoms, it can trigger a process known as natural microwave amplification by stimulated emission of radiation, or an astrophysical maser. In an astrophysical maser, an external energy source pumps hydrogen or hydroxyl molecules into an excited energy state, creating a population inversion. When a background photon of identical frequency, such as a 1420 MHz photon from the hydrogen line, passes through this population inverted cloud, it triggers a chain reaction of stimulated photon emissions. All the emitted photons share the exact same phase, direction, and frequency as the original photon. This process amplifies the 21 cm neutral hydrogen line into a narrow, intense, coherent radio beam. If this transient maser emission is simultaneously focused by diffractive interstellar scintillation as it travels through galactic plasma, the resulting signal arriving at Earth would appear as a brief, hyper-intense, narrow-band radio burst occurring at the exact frequency of atomic hydrogen. Furthermore, follow-up searches targeting the exact coordinates of the WOW signal in the constellation Sagittarius failed to detect any repeating emission. While early interpretations viewed this lack of repetition as evidence against an astronomical source, modern transient astrophysics recognizes that many energetic cosmic events, including non-repeating fast radio bursts, magnetar flares, and cosmic maser flashes, are naturally singular or possess extremely long, erratic duty cycles spanning decades. The physical analysis of the WOW signal illustrates the necessity of evaluating cosmic anomalies through the combined principles of quantum mechanics, plasma physics, and wave optics. The unique frequency of the 1420 MHz neutral hydrogen line, amplified by stimulated maser dynamics, and focused across interstellar distances by diffractive scintillation through ionized plasma, provides a comprehensive, physically grounded framework for understanding how nature produces extreme, fleeting radio anomalies. Rather than requiring artificial origins, the WOW signal stands as a testament to the complex, transient electromagnetic interactions operating within the interstellar medium of our galaxy. Modern observational cosmology relies on gravitational lensing as one of its primary empirical tools to map invisible mass distributions across the universe. First predicted by Albert Einstein through his general theory of relativity, gravitational lensing describes the deflection of light rays as they pass through a gravitational field created by a massive cosmic body. While light inherently travels along geodetic paths, the shortest routes through spacetime, the presence of matter bends spacetime itself. Consequently, when photons emitted by a distant background galaxy pass near a heavy foreground object, such as a galaxy cluster, their paths curve around the gravitational well. This curvature warps, magnifies, and multiplies the images of the background source, effectively turning foreground mass distributions into cosmic telescopes. Gravitational lensing operates across three distinct regimes: strong lensing, weak lensing, and microlensing. In strong lensing events, the gravitational field of a foreground cluster is so intense that it bends background light into striking geometrical shapes, including long arcuate formations, multiply imaged quasars, and complete rings of light known as Einstein rings. In weak lensing, the gravitational deflection is far subtle, producing slight statistical distortions in the apparent shapes and orientations of thousands of background galaxies. By measuring these minute tangential shear alignments across vast swathes of the sky, astronomers can reconstruct the total mass distribution responsible for bending the light, regardless of whether that mass shines or remains completely dark. This optical property of spacetime provided the definitive proof for the existence of cold, dark matter. In the early history of astrophysics, measurements of galactic rotation curves conducted by Vera Rubin revealed that the outer stars of spiral galaxies were orbiting at unexpectedly high velocities. According to Newtonian mechanics and Keplerian dynamics, stellar orbital speeds should decrease at larger radial distances from the galactic centre, where visible luminous matter is concentrated. Instead, flat rotation curves showed that stellar velocities remain constant out to the faint edges of galactic disks. This implied that galaxies were embedded within vast, spherical halos of unseen mass that extended far beyond the visible stars and gas. While rotation curves provided strong indirect evidence for extra mass within individual galaxies, skepticism remained regarding whether the discrepancy was caused by an invisible form of matter or by a breakdown of general relativity on galactic scales, such as proposed by modified Newtonian dynamics. Gravitational lensing resolved this fundamental debate by directly measuring gravitational mass independently of luminous matter and dynamic motions. Paramount empirical demonstration of dark matter through gravitational lensing occurs in the Bullet cluster, officially designated 1E0657-558. The Bullet cluster consists of two giant galaxy clusters that underwent a high-velocity, head-on collision approximately 150 million years ago. During this cosmic collision, the different constituents of the two clusters behaved in fundamentally different ways, based on their physical properties and interaction cross-sections. The luminous baryonic matter within galaxy clusters exists primarily in two forms: individual galaxies and the hot, ionized intracluster plasma. The individual galaxies occupy a small fraction of the cluster's volume, so during the collision, the stars and galaxies pass through one another without physical contact, moving through the impact zone almost entirely unimpeded, like sparse swarms of bees. By contrast, the superheated intracluster gas, which contains roughly 80% of all normal baryonic matter in the cluster, experienced intense fluid ram pressure and electromagnetic drag as the two gas clouds collided. As a result, the intracluster plasma slowed down significantly, heating up and stalling near the center of the impact region. X-ray observations conducted by NASA's Chandra X-ray Observatory mapped this decelerated plasma, revealing a distinctive bow shock wave where the bullet-like subcluster punched through the larger cluster's gas cloud. If visible baryonic mass constituted the total mass of the universe, the gravitational center of the bullet cluster system would reside precisely where the bulk of the baryonic matter stalled, at the central X-ray emitting plasma clouds. However, when astronomers performed a comprehensive weak gravitational lensing analysis of the bullet cluster using high-resolution images from the Hubble Space Telescope and Magellan telescopes, the resulting mass map revealed a completely different physical layout. The weak lensing maps demonstrated that the primary gravitational mass concentrations were situated not at the central, high-density X-ray gas clouds, but far to the sides, perfectly aligned with the collisionless, fast-moving individual galaxies. The light from background galaxies was bent most intensely around regions of space that contained almost no visible gas or baryonic matter at all. This spatial separation between the baryonic gas mapped by X-rays and the total mass mapped by gravitational lensing provided incontrovertible empirical proof for the existence of dark matter. It proved that the dominant mass component of the cluster consists of a collisionless, non-baryonic particle species that passed straight through the collision alongside the galaxies without experiencing fluid drag or electromagnetic interactions. The dark matter halos simply slipped past each other, carrying the majority of the system's gravitational potential along with them, and bending background light via gravitational lensing. Beyond the bullet cluster, weak gravitational lensing surveys on cosmological scales, such as the Dark Energy Survey and the Kilo-Degree Survey, map the large-scale distribution of dark matter across billions of light-years. By analysing the subtle shapes of millions of distant galaxies, these surveys reconstruct the three-dimensional cosmic web of dark matter filaments. The lensing maps reveal how dark matter acts as the primary gravitational anchor of the cosmos, pulling baryonic gas into its deep potential wells to seed the growth of galaxies and superclusters over cosmic time. The physics of gravitational lensing demonstrates how light acts as an absolute tracer of space-time curvature. By measuring the precise deflection angles of photons emitted billions of years ago, astrophysicists can map the invisible contours of dark matter, proving that the vast majority of mass in the cosmos remains completely hidden from direct optical view, revealing its presence solely through the bending of light. While gravitational lensing maps the invisible distribution of cold dark matter on galactic and cluster scales, observational cosmology faces an even larger, mysterious driver operating on cosmic scales: dark energy. On macro-scale distances spanning billions of light-years, dark energy exerts a pervasive outward push that actively counters gravitational attraction. Rather than slowing down under the collective pull of all visible and invisible matter, the expansion of the universe is accelerating. The discovery of this cosmic acceleration fundamentally altered our understanding of thermodynamics, general relativity, and the ultimate fate of space and time. The observational foundation for the accelerated expansion of the universe was established in 1998 by two independent research teams, the High-Z Supernova Search Team and the Supernova Cosmology Project. Both teams utilized Type 1a supernovae as standard candles to measure cosmic distances across vast redshifts. A Type 1a supernova occurs in a binary star system when a carbon-oxygen white dwarf accretes mass from a companion star, approaching the Chandrasekhar mass limit of approximately 1.4 solar masses. At this critical threshold, electron degeneracy pressure can no longer balance gravity, triggering a runaway thermonuclear explosion. Because every Type 1a supernova explodes at roughly the same mass limit, they all exhibit a remarkably uniform intrinsic luminosity, making them ideal distance indicators across cosmological space. By measuring both the apparent brightness and the redshift of dozens of distant Type 1a supernovae, astronomers mapped the expansion history of the universe. If the universe contained only matter, both baryonic and dark matter, the cumulative gravitational attraction of all cosmic structures should gradually decelerate the cosmic expansion rate over time. Under a decelerating expansion model, a supernova at a specific redshift should appear brighter and closer to Earth than it would in a continuously expanding universe. However, the empirical measurements revealed the exact opposite result. Distant Type 1a supernovae was systematically fainter and significantly further away than predicted by any decelerating cosmological model. The light travelling from these distant stellar explosions had taken longer to reach Earth because the space between galaxies had stretched at an increasing rate during the journey. This landmark discovery proved that approximately 5 billion years ago, the expansion rate of the universe ceased decelerating and began actively accelerating. To describe this cosmic acceleration within the framework of Einstein's general theory of relativity, theoretical physicists analyzed the stress-energy tensor through the Friedmann equations. In general relativity, the acceleration of the cosmic scale factor depends not only on energy density, but also critically on pressure. The second Friedmann equation demonstrates that the acceleration of space is proportional to the energy density plus 3 times the pressure of the fluid filling the cosmos. Under standard physical conditions, ordinary matter and radiation possess positive energy density and 0 or positive pressure. Positive pressure contributes to attractive gravitational deceleration. However, if a component of the universe possesses a negative pressure equal in magnitude to its energy density, the pressure term inside the equation becomes strongly negative. This negative pressure generates a repulsive gravitational effect, driving space to expand at an exponential rate. Dark energy is precisely this physical fluid, an exotic form of energy characterized by uniform spatial density and persistent negative pressure. The simplest mathematical formulation of dark energy is the cosmological constant, denoted by the Greek letter lambda. Originally introduced by Albert Einstein in 1917 as a static term to balance gravity in his field equations, the cosmological constant represents a uniform vacuum energy density inherent to space itself. According to quantum field theory, empty space is not a void, but a dynamic quantum vacuum filled with virtual particles constantly popping into and out of existence. These zero-point quantum fluctuations generate an intrinsic energy density attached to every cubic centimetre of space. Because the cosmological constant represents an intrinsic property of space, its energy density remains constant as the universe expands. As normal matter and dark matter dilute and become less dense over time as the cosmic volume increases, the density of dark energy remains completely invariant. Approximately 5 billion years ago, as the matter density dropped below a critical threshold due to ongoing expansion, the constant energy density of dark energy became the dominant driver of the cosmic energy budget, switching the global acceleration of the universe from negative to positive. Currently, precise measurements compiled by cosmic microwave background observatories, such as the Planck satellite, indicate that dark energy constitutes approximately 68.3% of the total mass energy budget of the universe. Dark matter accounts for roughly 26.8%, while normal baryonic matter, atoms, stars, planets, and gas, comprises merely 4.9% of existence. To evaluate whether dark energy is a true static cosmological constant or a dynamic scalar field that changes over time, cosmologists utilize the equation of state parameter, designated as W. The equation of state parameter is defined as the ratio of pressure to energy density. For non-relativistic matter, W equals 0, while for relativistic radiation, W equals 1/3. For a static cosmological constant, the equation of state parameter W is exactly equal to -1. Alternative dynamical dark energy models, collectively known as quintessence, propose that dark energy is not an immutable vacuum property, but rather a slow-rolling scalar field propagating through space. In quintessence models, the equation of state parameter W can evolve across cosmic time, varying slightly above or below -1. If W drops below -1, a scenario known as phantom energy, the acceleration of space will eventually grow so violent that it will tear apart galaxies, star systems, planets, and even individual atomic nuclei in a catastrophic scenario known as the Big Rip. Observational surveys tracking large-scale cosmic structures, galaxy cluster abundances, and baryon acoustic oscillations, such as the Dark Energy Spectroscopic Instrument, continue to measure W with increasing precision. Current datasets remain consistent with an equation of state parameter W extremely close to -1, supporting the classical model of the cosmological constant driving cosmic acceleration. The physics of negative pressure and dark energy reveals that the ultimate fate of the universe is governed by an invisible, space-filling field. As dark energy continues to accelerate the expansion of the cosmos, galaxies outside our local, gravitationally bound group will eventually be pushed beyond our observable cosmic horizon. Over hundreds of billions of years, the night sky will grow increasingly sparse, leaving our galaxy isolated in a vast, cold, and dark expanding void. Understanding dark energy remains one of the greatest challenges in physics, bridging the vast macro scales of cosmology with the quantum mechanics of empty space. As we journey across the cosmos, from light-swallowing exoplanets and horizontal glass storms to supermassive black hole eruptions, dark matter scaffolding, and the mysterious negative pressure of dark energy, one fundamental truth becomes clear. Our current understanding of the universe is merely a brief glimpse into an infinitely complex reality. Every discovery we make inevitably brings forth new questions, challenging the traditional boundaries of physics, chemistry, and astronomy. The strangest things we have discovered in space serve as a humbling reminder of how much remains hidden in the dark, waiting for future technologies and scientific breakthroughs to illuminate. Humanity is only beginning to unravel these cosmic mysteries. As our telescopes peer deeper into the fabric of space and time, our models will continue to evolve, continuously rewriting what we know about the architecture of existence. The cosmos is not a silent, static background, but a dynamic, violent, and endlessly fascinating laboratory of physics, operating at scales beyond human imagination. If you enjoyed this deep scientific exploration into the strangest discoveries in space, and want to continue uncovering the vast secrets of our universe, please take a moment to like this video and subscribe to the channel. Your support helps us bring more grounded, high-level scientific content to curious minds around the world. We would also love to hear from you. Drop a comment below letting us know where in the world you are watching from and what time it is wherever you are right now. Thank you for listening, and until next time, keep looking toward the stars.